Calculating gradient. Step 1. Write the formula, which is gradient equals the change in field value divided by the distance. If you forget the formula, it's on page 1 of your Earth Science reference table. Step 2. Substitute in the values for the equation. So you have the values for your field value, you have your values for the distance. Step 3. Calculate the gradient. It's a simple division problem. Change in field value divided by distance, and to get the change in field value you have to subtract the smaller value from the larger value. So a simple subtraction and then division problem. Finally, the answer must include units. Okay, let's take a look at a regions question right here. What is the gradient along the straight line between points A and B? Well, step 1, write down the formula for gradient. Gradient equals the change in field value divided by the distance. Step 2, calculate the change in field value. A is equal to 400, B is equal to 300. The change from 300 to 400 is 100. So the change in field value is 100 feet. Now if you see, how did I know it was feet? Well, if distance is in miles, the elevation will always be in feet. If distance is in kilometers, the elevation will be in meters. Next step, calculate the distance. So we measure this distance along AB, and we bring that down to the scale, and we see that it's 4 miles. The distance equals 4 miles. So we now have our gradient equals change of field value, which is 100 feet, divided by the distance, which is 4 miles. So our gradient equals 100 feet divided by 4 miles. Our gradient equals 25 feet per mile. Okay, let's do another problem. We want to calculate the gradient between x and y. Now, I want to zoom in a little bit because it's difficult to see x and y. I've highlighted them right here so you can see that. But if we can zoom in a little bit, then we can see x, the value of x is 13, the value of y is 25. So the change in field value is going to be 25 minus 13, and that's going to be 12. So remember, the equation for gradient is change in field value, which is, in this case, 25 minus 13 divided by the distance. So to get the distance, we measure between x and y, and we move down to our scale, and we can see that, oh, it's 0.4 miles. So the distance equals 0.4 miles. The change in field value is equal to 25 minus 13, which is 12 feet. So our equation for gradient is change of field value divided by distance. That's going to be 12 feet divided by 0.4 miles. Well, let's get rid of this decimal point, and so that would be 120 feet divided by 4 miles. 120 divided by 4 is 30, so the gradient is 30 feet per mile. Okay, let's do another problem. This is another map, it's another regions question, and what compass direction is Aurora Creek flowing? Well, there's Aurora Creek, I've just highlighted it for you, and down on the right you can see the compass direction is on your map. So the first step is to look at the contour lines. I've highlighted one of the contour lines so that you could see the contour lines point upstream. There it is, and the river therefore is flowing the opposite direction, down and to the right. Well, we know what the compass direction is, so down, up is north, down is south, right is east, so this is going to be down and to the right would be southeast. What compass direction is Aurora Creek flowing? It's flowing to the southeast. Also, as you know, rivers typically flow into large bodies of water. And you could also have looked at the contour lines. Rivers flow downhill. Contour lines are pointing to the right, which is east. So the river is flowing to the left, which is west. If you look at the elevation of these contour lines, this elevation here is 20 feet. This one up here is 50 feet, 40, 30, 20, 10, and it's flowing, so the river is flowing downhill into the ocean. So that also tells you it's flowing from right to left, which is west. Third of all, you know that rivers flow into the ocean. So every single case, you know the river is flowing from right to left, which is west. This is a very typical question that you'll see on the Regents exam. They're going to show you a simple contour map, and you have to determine which way the rivers are flowing. So the first thing we do is look down here on the right, and you can see tells you which way north is. So that N with the arrow tells you that north is up, south would be down, east is to your right, west is to your left. Now we go to the contour lines and we mark them so that we can see which way they are pointing. So I'm marking the contour lines on the Sapphire River, and you can see that the contour lines point upstream. And now I'm marking the contour lines on the Garnet River, and again, the contour lines point upstream. So these green lines are pointing upstream. The contour lines are pointing upriver, so therefore the river is flowing the opposite direction. Looking down on the right, we see that north is up, east would be to the right, so the rivers are flowing to the east. According to the map, toward which compass direction did the ice lobe flow over the Catskills? Well, this map doesn't tell you where the Catskills are. If you don't know where the Catskills are, you need to use your Earth Science Reference Table, the landscape region. Okay, this is the generalized landscape regions of New York State. The Catskills are right here in New York. So the Catskills are right here. The direction the ice was flowing is this direction. You see these arrows right here. And over on the right of the map, you see where it says this north right here? This gives you the key. So up is north, to the right is east, to the left is west, to the bottom is south. So this is moving from the top right to the bottom left, or from northeast to southwest. You can answer this in several ways. You can say the ice was moving from the northeast to the southwest. That would be one good answer. Or you could say that the ice was moving southwest. Okay, this line here is 0 degrees. I've just highlighted the 0 degrees. I've just highlighted the line. And that's latitude. Latitude lines run left and right. If you go up and you look at your longitude, to the left of 0 is west, and to the right of 0 is east. So the west longitude's over here. We want 40 degrees. That's this line right here. And now where they intersect is right here, and that's where you should click. That's 40 degrees west longitude, 0 degrees latitude. On the diagram in your answer booklet, place an X at 15 degrees south, 30 degrees west. Okay, this line right here is the equator. Everything down below the equator is south latitude. So this 15 degrees right here is south latitude. So 15 degrees south will be on this line. Now what we have to do is find west. Alright, so everything they're showing us here is west. 0, 15, 30. And here's 30 degrees west. Here's 15 degrees south. The X goes right here. They want 30 degrees north latitude. I've just shown you north is all the latitudes above 0 degrees. South are all the latitudes below 0 degrees. So 30 degrees north, I've just highlighted the 30 degrees, and it'll be this line right here. That's your 30 degrees north latitude. And then they want 40 degrees east longitude this time. So again, if you look on top, everything to the right of 0 is east longitude. 40 is this one right here, which I've highlighted. Where these two lines intersect, that's where you would click. That's going to be 30 degrees north latitude, 40 degrees east longitude. State the latitude and longitude of Northridge, California. Include the correct units and compass direction in your answer. Well, I'm highlighting the horizontal line at 34 degrees north. That's your latitude, and you can see that runs through Northridge. Now I'm highlighting the vertical line through Northridge, and you can see it's not quite on 119 degrees west. So let's look over here. Here's 117 degrees west. Halfway between would be 118, and then you'd have 119. So this is much closer to halfway between 118 and 119 degrees. Now degrees, just like minutes, there's 60 of them because you're dividing up a circle. Remember, a circle has 360 degrees. So we have 60 degrees, and so half of 60 degrees would be 30 degrees, just like half an hour is 30 minutes. So I would say that this is 118 degrees, 30 minutes west. So our latitude and longitude, 34 degrees north, 118 degrees, 30 minutes west. This map shows the average number of thunderstorms during the year in the continental United States. Which New York State landscape region normally experiences the most thunderstorms? Okay, so we're going to look at New York State. New York is in the upper right of the United States. I'm going to blow that up right now. I've blown up the region that has New York State up so that we can see it more clearly. And you can see there's three lines here. There are 20, 30, and 40. These lines are the average number of thunderstorms each year. So as you can see, this part of New York is between 20 and 30 thunderstorms each year. This little sliver down here is between 30 and 40 thunderstorms each year. So therefore, this little sliver is going to have more thunderstorms than the rest of New York. Now I'm going to try to overlay the landscape region map from your Earth Science reference table, and we can see that this region with 30 or more thunderstorms is the Allegheny Plateau. So looking down at your possible answers, you can see answer number 1, I've just highlighted it, Allegheny Plateau. That's your answer. The next question. State a possible elevation of the top of Patriot Hill. Well, Patriot Hill is down here on the left. I've just highlighted it. And when they say possible elevation, that could be the lowest possible, the highest possible, or anything in between. Okay, so let's look at this slide. I've highlighted the contour interval, which is equal to 20 feet down on the bottom left. And then I've highlighted this contour line 600, and the interval is 20, so the next one was 620, 640, 660, 680. It's kind of hard to see, so I'm going to expand this. Let's zoom in so we can see this a little easier. You can see that the top of Patriot Hill has to be greater than 680, but it can't be 700 because there'd be another contour line. So the possible elevation is anywhere more than 680 and less than 700. So it could be 681 to 699. Any number in that range is an acceptable answer. The next question. State a possible elevation of the top of Patriot Hill. Well, Patriot Hill is down here on the left. I've just highlighted it. And when they say possible elevation, that could be the lowest possible, the highest possible, or anything in between. Okay, so let's look at this slide. I've highlighted the contour interval, which is equal to 20 feet down on the bottom left. And then I've highlighted this contour line 600, and the interval is 20, so the next one was 620, 640, 660, 680. It's kind of hard to see, so I'm going to expand this. Let's zoom in so we can see this a little easier. You can see that the top of Patriot Hill has to be greater than 680, but it can't be 700 because there'd be another contour line. So the possible elevation is anywhere more than 680 and less than 700. So it could be 681 to 699. Any number in that range is an acceptable answer. What is Earth's rate of rotation at point Y in degrees per hour? Point Y is right here. Now, the Earth's rate of rotation, regardless of where you are on the Earth, is going to be 15 degrees per hour. That is the answer. However, if you forget this, all you have to do is remember that the Earth is one day is 24 hours long, and a sphere has 360 degrees. So if you divide 360 degrees divided by 24 hours, you will get 15 degrees per hour. This is a field map. It shows the water depth in feet, presumably of a lake. And suppose you'd been on a boat all day taking measurements. You'd measure the depth, and then you find your location, and you plot it on the map. And so you've taken a whole day's worth of data, you've come back, you plotted this on a map, and now you want to convert this into a contour map that you can read. And that's what we're going to be doing right now. And as a scientist, you would do this many times. You might do it for the depth of a lake or the elevation of a hill. You could also do it for air pressure, temperature. I mean, you could do it for a number of different data readings that you might take. So a field map is just a map in which you've collected data, and now we're going to map this data. So the first task we have is to plot the contour line for 20 feet. First thing I'm going to do is I'm going to show you that on this map there's a couple of points that are 20 feet, and I'm highlighting them. But you realize there's only a couple, because when we were taking the data, we weren't trying to get any specific depth. We were just collecting our data. So now we have to figure out where 20 feet goes. And if you look at our 20-foot mark, it's between 19 and 21 or 19 and 25. If you're 19 feet deep in a lake and you're 25 feet deep in a lake, somewhere in between, you're going to be 20 feet deep. And so now I'm going to go in and I'm going to put the points in for you. Okay, so I'm going to put in a point right over here, and as you can see, I put it between 18 and 21. Now 20 is closer to 21, and so therefore I put my point a little bit closer to 21 than 18, not exactly halfway. Then you can see over here between 17 and 21 I put a point. And then down here between 16 and 25, 20 is about halfway, I put the point about halfway. And here between 15 and 26, 20 is slightly closer to 15, so my point is slightly closer to 15. And then 17 and 29, 20 is much closer to 29, so I put the point there. And let's go to the other side, 19 and 21, 21 and 18, 18 and 21. Now over here you see 18 and 23, 20 is about halfway, 17 and 21, and then 13 and 23. Once you put in all your points, connect them with a line. And once you've connected all the points with a line, you need to label it. In this case would be 20.